Yes, hello everyone. My name is Ben. I'm the CTO at Pometry. I'm also in charge of the coffee, and I'm joined by our democratically elected head of engineering, Fabian. And I want to talk about temporal graphs and what we do at Pometry. So instead of just focusing on people that write queries, one of the sort of main areas that we work out at Pometry is with data scientists that are much more happy with pandas, square brackets, and sort of weird access patterns, and writing ML pipelines. And typically in this space, the graphs are very small. No one really likes using network X. So one of the things that we want to be able to do is work on humongous graphs on itty-bitty machines. So as Max pointed out earlier, we do stuff like a 3 terabyte graph, 20 billions of edges on like a MacBook. The other side of this, obviously, because we work with data scientists, is we are a Python library, can run this nice and embedded. If you want to write your own wonderful subroutines, this is available in Rust. You can compile your own version of Reftory. And this is mainly accessed via our sort of Python first approach, but you can actually host this as a server where you can query and visualize your graph. So the second side of this is that, in my opinion, some of you may disagree, I don't think data graph tools deal with temporal data very well. So you might have some that have a couple of snapshots, perhaps, but when it comes to like, I want to do some sort of time series analytics or I want to do temporal analytics, this is just fucked, to be honest. It's just not really available at all. So we want to be able to provide this. And the reason for this is that I like to think about data really as like a story. I want to be able to see how we've kind of evolved to get to where we are now, and then use this to kind of, where are we going next? So if I think about a real story, say the Lord of the Rings, if I had 2 snapshots where Gandalf is, in the Shire, and then all of a sudden he's off with Aragorn and Legolas, I've got 2 pages of a whole book, no bloody idea what's going on. And so what I want to actually be able to do is, where was Gandalf at every single point in time? Can I freely move between these versions? Can I have a look at this as a time series? And this gives me a lot more freedom in kind of combining the wonderful structure of networks with this kind of time series component, which gives you like a really great way of defining behavior. So what we typically end up doing is we'll take this set of tooling and we'll build a graph very quickly from some random compilation of data, and then extract out a load of features and pipe these downstream to either other ML tools, or more recently, we've been building a set of tooling around this where you can define risk patterns and then extract these risk patterns in a set of subgraphs. So this is a Reftory server running where we have about 300 million transactions in, and we've extracted out a load of different patterns of interest. So we have things like, I don't know if you can see at the back, but scatter-gather patterns, funneling patterns, odd hours of movement chaining, so temporal cycles and so on. And if we were to click on one of these graphs, or my previous self clicks on one of these graphs, we get something that looks like this, where we have in the middle here a cryptocurrency exchange. So this is actually what Amin was pointing out on some of the financial transactions. And we've got some sort of mixture of patterns that this exchange has been involved in. So we've got like a scatter-gather pattern, which hopefully my previous self will wonderfully click and highlight. Hooray. There we go. Up here, so this person has sent money out to 4 people, which have sent that into the exchange. And then on the other end, we've got a temporal cycle where someone's received money from the exchange and then sent that round back to themselves and sent it into the exchange again. So what this means is this exchange has either got terrible KYC, or know your customer checks, or is actively involved in these processes. And so with our pipelines, it's very easy to kind of both extract these from very large corpuses of data and then actually visualize them as well. The other side of this, which you may not be surprised about to hear, is that most of our users love the risk engine. They love to be able to extract these things, but most of the business people don't want to write Python. Shock horror. So what we've also done then is to add natural language interfaces where, I don't know if I can actually zoom in here, can I? No, I can't. So what this says is generate me a KYC report on Stellar Innovations, its directors, and any risks they are known for. So what this will do is it will go into the graph, it will find relevant entities, in this case, Stellar Innovations, it will find Stellar Innovations directors, suspicious activity reports, etc., as well as all these risk triggers that we've written as part of our pipeline. And then we'll give you, via our document representation of those nodes, a nice summary. And then alongside this summary, which may be useful, you may decide to push this up the chain. You can then go and grab these nodes in the graph and go back and check them. So I think my previous self here is going to click on Gay Siraji, who's our bad director at Stellar Innovations, open him up, and then go and explore in the graph view. So from here, you can then check, Is he actually a director of Stellar Innovations? Is he does he have these suspicious activity reports? Is he a generally dodgy guy? And so this kind of gives you this provenance to be able to check back through and make sure that the answer that you've got is correct. And with that, this is a very top level version of Pometry. I'm going to skip out the middle where we talk about the Python APIs if anyone's interested in that or the Rust stuff. And I'm going to hand over to Fabian, who's going to dive incredibly deep right to the bottom. I'll jump over to the side.
Hello. Right. So when I joined, when I started helping Pometry with the storage and with their overall architecture, we were distributed. We were in Akka. We had some attempts on using Kafka and what was the other one? Pulsar to ingest data. The problem is very quickly we were hitting the JVM garbage collection explosion. There was a lot of complexity in our distributed code. Often we were like, oh yeah, we can run on 4 boxes, but the overall timings of the algorithms were pretty poor. Alphabay is a darknet market that dealt in drugs. It was shut down by the federal government. But the data set we had access to the data set and we were trying to load it and we were struggling to load 1 gigabytes in 122 EC2s. So we tried for a while to use Arrow. Somebody built a storage on the JVM, but if you ever want to, hurt yourself, use Arrow on the JVM. It is horrendous. And because of the top level requirement that data scientists like Python for some god awful reason, marrying the JVM with Python is another nightmare that I only wish upon my worst enemies. So these were the issues we were dealing with. So come January 2020, I think 2021. I kind of said, okay, screw all that. That's terrible. So there are a few decisions we took. Number one, we dropped the distributed. And there's a big discussion about why did we do that. The TLDR is that you can today get a box with 4 sockets and hundreds of cores, 8 terabytes of RAM, maybe more, and 1 petabyte of NVMe storage, which is enormous. So we were like, we're not going to deal with distributed. The second one was that Rust is a lot better than the JVM when it comes to memory. Unbelievable, like no comparison. And the PyO3, which is a layer that basically allows you to write Python, but in Rust. So we don't have a single line of Python in our code other than the tests. All of it is driven from Rust, but the library is a Python library, which makes me happy because I don't like Python. So we started with just some basic data structures, some basic ideas, and we were able to breeze through the Alphabay data set. We were like in the hundreds of millions of edges, together with property history, any type of properties you want. So I don't know, JSON or not, it doesn't matter. But it doesn't come for free. Like you can get yourself in a point where you over allocate with Rust, so you have to think a little bit about it. And we try to do some benchmarking and try to get better at memory usage. But eventually, like the graph can get big enough, and you run out of RAM. So this right now is the state of the open source Raftery. It's all in RAM. It's all in RAM. But we were given some very, very, very large graphs. As I feel like every time I break a boundary, either Hamza or Ben is it just 10x it for me, and it's great. So we said, okay, forget about the writing and the mutability of it. Let's just think about analytics. Let's just have something that can address a humongous graph. A humongous temporal graph. So there are a few things. We know CSR beats everything, like hash maps, B trees, did anything. It's not comparable. It's just, it goes, the CPU loves it, and it just works. Rust has this thing called Rayon, which is parallel processing. If you've ever had the pleasure, you basically write, it has the semantics of iterators, except it goes in parallel. The next thing we did is, like, in order for us to be able to load graphs with a limited amount of memory, we had to shard everything. And by that, like, there are many dimensions to a graph. They're like, the shard the number of nodes, we break them down into chunks of k nodes. Shard the number of edges, the same thing. But you have to shard also the adjacency lists. You have to shard the offsets. Basically, break everything down into small manageable pieces, so that when you load a graph that is like the network graph, that like the LANL graph, how they call that?
Yeah, so we have a network, a graph of 20 billion interactions between servers over 90 days. So this is the unified host and network data set. It's free to pick out if anyone wants to play with it. You need to give an email, then they'll send it to you. About 3 terabytes of data. And you have nodes in there that are connected to every other node. They're like the DNS server talks to everyone all the time.
Exactly. So you have really pathological entries that we wanted to support, like, and like the DNS and like the static graph, that like the one without the properties in LANL, in the unified host network, is about 1 million nodes and a few thousand and a few, I don't know, million edges. But because we separate, being a temporal graph database, we separate the static graph, the one that has only constant properties, from the properties that are temporal, which means that we are basically a graph squared, right? Every node has properties and edges that have an existence defined by timestamps. So what this allows us to do is to effectively go at any point in time and see how the graph looks like. We also wanted to, so these are some of the stats. We also want to be able to load the graph like this. It's just basically we have graphs that are 2 terabytes. We have graphs that are 100 billion edges. We load them instantly. Basically, we just address them. When it comes to actually ingesting the graph, that's what I mean here on loading. When it comes to ingesting the graphs, we have a pipeline with one of our customers that they ingest in a like 20 minutes graphs that are 2 terabytes in size. They run the analytics on them, and they just throw them away afterwards. We have done a test currently with the Graph 500 at 100 billion edges. The cost of us running this on EC2 is, again, very small. You do not need a 1,000 machines cluster to go distributed to run these things. We just work with whatever we have. The more memory you have, the better. If you don't have all that memory, I mean, Hamza's done presentations in front of people running on his MacBook with graphs that were a terabyte large, and he's able to explore them. You're not going to get the best performance, but you will definitely run. I cannot stress how amazing NVMEs are. Like, they're like the most fantastic thing since DRAM. Like, it's like I don't know, they're incredible. This means that, you know, a data scientist does not need a hypercluster to look at very large graphs. What we do is we have these views on top of the graphs. And you can combine these in any way, in any direction. You can say, I want to see the structure of the graph and the properties between time I and time j, wherever. You can say, I want to see the graph at a specific time k, and only that. When you ask for the property, in our API, when you ask for the properties, for a temporal property, you don't get a value. You get an iterator of values. You can ask for the last one, you can ask for the earliest one, or see all of them. We have layers, which are essentially subgraphs where the nodes maintain identity. So node 5 is node 5 in all the layers, but it could have different properties across layers, and it has different adjacency lists across layers. They're effectively separate subgraphs. It's just that the node maintains identity. So you can do some lookups in one layer, and then go in another layers and in another layers and see what's happening over there. We have a property view. You can say, only show me nodes or edges that have these properties, and you can mix these. There's one thing that we do to improve computation is like you can apply these views in any direction, then smash them together. We create a materialized view that is very cheap to sort of create, and it occupies very little memory. And then you do your computation on that, and that materialized, you already know what edges and what nodes are present in your graph. So this was quite like a shock for not a shock. It was quite impressive for us to see how quickly you can, with these materialized graphs, you can operate on them, because effectively, right, we have a bit mask over the edges in the nodes, and go, yeah, we